Okay. Actually, I have a few things left over to say from my first hour, so I want to spend a little bit of time telling you some more about these representations before I go on to the deformations of these universal enveloping algebras. More specifically, we'll be quite interested in the notion of character of a representation. So let me give a definition for that. So if V is a representation which I can split as the so-called weight spaces. So here I redo a smaller example. Here the weight spaces are one-dimensional and two-dimensional. This is a two-dimensional weight space. It's like the stuff that lives at that particular weight. Then we can talk about, let me make a definition that I had forgotten to make. That's the so-called Cartan subalgebra. So if you look at these h's correspond to linear functionals on this space that I'm drawing the picture on. For example, h1 is this linear functional where I've given some values of this functional, and I give them so here it's like positive there and negative there. So it's a dual of an element in the dual of the space in which I draw. The space in which I draw is lambda, or maybe the vector space that's around lambda, so lambda tensors R, that's the dual. And then you take this. Okay, that's an aside. Okay, the definition starts here and continues there. So the character of V is an element of the space of functions from H to C, and is defined to be evaluated on a point T So it's a function whose role in life is to keep track of the dimensions of these weight spaces. These weight spaces have dimension 1, 1, 1, 2, 1, 1, 2, 2, 1, 1, 1, 1. Well, you want to keep that information somehow, and then you package it into a function, and that's a character. And the character has exactly that information. Yes?
The symbol under the direct sum to be a lambda? Or what is the V that you're summing?
Oh, sorry. This here is lambda. Yes. Thank you. So this corresponds to that. In certain cases, we'll be interested in representations that are infinite dimensional. For example, the Fermat modules. And we want to extend this notion to that situation. And okay, you can just write down this formula as is. But what might happen is that you might have a situation where this sum is divergent. And therefore, for infinite dimensional representations, then we make a slight extension So suppose I want to compute the character at a particular point t, and that at that point the thing diverges. But suppose that I'm lucky and there exist other t's where the thing does converge and defines a function which is analytic, then, well, I define this to be the analytic continuation of what it is in the place where it converges. So anyways, that's the formal definition that I'll be using. But actually, I don't want to bother with all that notation, and I will write things in the following way. So this is the notation that I will be using. I will just write e to the mu, or actually what I mean is this function e to the mu paired with t, where t is an element of this. And the good thing about this notation is that you can use it formally as if it's just exponentials and not worry about exactly how things look like. It just works out. The notation is good notation. So we care about the characters of these L lambdas because they eventually contain a lot of information about the structure of these L lambdas. But it's difficult to get a hold on them directly, and it's better to first say something about the characters of the Verma modules, which is, by the way, the reason why we need this extra condition, this extra notation, extra definition. And so the Verma module, M lambda, there's a theorem called the Poincaré-Birkhoff-Witt theorem that, phrased in a sort of not very precise way, says that M lambda looks like the symmetric algebra on the underlying vector space of N. So this does not use the Lie algebra structure. And what it actually means, well, it means lots of things. It means that there's a filtration on this whose associated gradient is isomorphic to that, but that's not what I really want. I just want to know something about the dimensions. What it means is that if you look at the dimensions of the weight space here, it's the same as the dimensions of the weight space there that you find, with a slight difference that for M lambda, you start here on the top. M lambda starts there and goes that way, whereas the symmetric algebra would be more naturally placed in the middle. It starts in the middle and goes left and down. So at the level of character, what this ends up meaning is that the character of M lambda is the character of the symmetric algebra on the negative nilpotent up to this shift of lambda. This character is now easy to compute because you know what, I mean, this is a polynomial algebra. You can, you know how to, I mean, once you have a basis for n minus, you can write down a basis for the polynomial algebra and you can compute dimensions. And what you end up with is that it's a product of things like that. So each basis element of n minus will have weight minus alpha for a given positive root alpha. Well, it's the negative roots that are relevant, but I index things by the positive roots and then I put a minus. And then you have this element, its square, its cube, and so on. And then you take the product over all these things. Well, that's a power series which is sometimes convergent, sometimes not convergent. But when it's convergent, I know what it is. That's what it is. So we've computed the character of this Verma module. Now we care about the character of L lambda. So it's going to be convenient to extend the definition of L lambdas to also include the case when lambda is not a dominant weight. So L lambda is no longer going to be finite dimensional. It's going to be, we have the highest weight vector, and you mod out by everything that cannot go back to the highest weight vector by means of raising operators. That's a definition, and you get something which is sometimes finite dimensional, sometimes not finite dimensional. Actually, it's finite dimensional precisely when lambda is a dominant weight, precisely when these numbers are positive. One can also describe L lambda as, in a more explicit way, to say it's a span of well, this was the previous definition. Now we need to say, to only mod out by those that happen to be submodules. And that's the ones, so it's the set of I such that Si acting on lambda is actually smaller than lambda. So you mod out by all those things that happen to be in there. And the ones that are not in there, well, you don't mod out by them because they're not in there. I didn't introduce an important concept, which is the concept of Weil group. The Weil group W is the group generated by these reflections Si. It's the group of symmetries of this picture. In this particular case, the Weil group has order 6. You have reflections like that and reflections like that, and you let them generate something, and you get a group of order 6. The order of the Weil group depends on which Dynkin diagram you started with. So this is an action of the Weil group on the set of weights. It's this shifted action that I defined earlier. So let's ask the question, which Verma modules can one find in there? And these are some of the Verma modules. But then, well, suppose I start with M lambda, I find this guy inside it. Then I can ask, are there any Verma modules sitting inside that one? And that's something that you get by applying yet another reflection. So there is a proposition, which is non-trivial. I won't show it. I'll just give you the result, which is that all the irreducible representations that come in the So I want to decompose this guy into reducibles. Well, it's not really a direct sum, but I want to find a filtration, and I want to ask what are the reducible pieces that show up in the associated gradient for this filtration. Well, certainly, M lambda is showing up in M lambda, and that's irreducible. But then I have also all the irreducibles that show up in here. So I have L sub SI bullet lambda that shows up. And then I have the irreducibles in there, and you go on and you go on, and you find more things, but the statement is that that's all you find. You have nothing else. So, I mean, I'm not claiming to have given a complete argument for that, but this is something that I'm going to use to compute the character of L lambda. So what does that imply? It implies that there exists a formula right? I mean, if I have as a decomposition series for M lambda, then it means that the characters of this M lambda is the sum of the characters of the corresponding L lambdas that show up in this decomposition series. I don't know exactly how many there are. What I do know is that they are indexed by this set. The only ones that do show up are the ones where lambda prime is smaller. Otherwise, well, otherwise you'd fall outside. And I also know that B lambda lambda is equal to 1. Let's put these B lambda lambda primes into a matrix. Then this says that this vector is this matrix times that vector. We can invert the matrix. It's a triangular matrix, so it's invertible with ones on the diagonal. So the inverse is again triangle with ones on the diagonal. And what we find is a similar expression that expresses the character of L lambda as a sum over lambda prime equals now another matrix, the inverse matrix, lambda lambda prime, character of M lambda. And I also know that A lambda lambda prime equals 1. And that's pretty good, because we know what these guys are. They're given by this formula. So we have already a pretty good idea of the kind of formula to expect for these characters. So let's use the following ingredients to compute the character. I'm going to use this. I'm going to use that. And I'm also going to use the fact that the character of L lambda is invariant under the Weil group. The character is this way of encoding these dimensions here. And these dimensions are invariant under the Weil group. If you remember in the previous picture that I had last hour, I had these red arrows and green arrows. The red arrows form SL2 strings, for like little strings that are symmetric along this axis. The other ones form little strings that are symmetric along that axis. Therefore, the whole picture is symmetric along the group generated by those two reflections, meaning it's invariant under the whole Weil group. So that's the other piece of information that I will use, which is that okay, so we have these pieces of information. Let's now do some algebra and get what we want. Okay, we pull our sleeves and just go. So this is a sum over all lambda prime of the form W acting on lambda. That's this shifted Weil group action. A lambda prime character of M lambda prime. I can rewrite it as a sum over the Weil group. Well, let me rewrite these coefficients as depending on the Weil group, as opposed to depending on lambda prime. I mean, lambda is fixed. So e to the W acting on lambda okay, I just took this formula and put it in there. Now let's use the invariance under the Weil group. So we know that this is the same as, well, for each I, we know that this is the same as Si acting on this whole thing. So I copy the whole thing. Let me put now the Si inside the formula. So the sum over the Weil group remains AW E Si W. So this is a bit annoying. Both Si and W live in the Weil group. W acts via the shifted action, and Si acts via the non-shifted action. So bullet here, no bullet there. Very good. We're not done yet. So we would like to replace this by the shifted action, because then we know that it's just the shifted action of SIW on lambda. But there's a price we need to pay for that, which is that there is a factor e to the alpha I that comes out. Let's look at this. Here we have the set of all positive roots, and we're doing a reflection on that set. And it turns out that if you do a reflection on the set of all positive roots, the only thing that happens is that the root along which you reflect ends up going the other direction, and the other roots get permuted but remain positive. So I can rewrite this as a product over everything but alpha I being the root corresponding to the simple root corresponding to Si. Same expression. And then, well, this term, I take it out and put it here, and it becomes e to the plus alpha I. It was e to the minus alpha I, and now it becomes e to the plus alpha I. Well, what is that quotient here? E to the alpha I divided by 1 minus e to the alpha I. That's the same thing as minus, let me just write it. It's the same thing as, there's a minus 1 that comes out there. There's this sum. Let me re-index the sum so that, so this here is just SIW acting on lambda. And I can reorder the indexing so as to put this thing here and that remains without. So A sub SIW e to the W shifted action on lambda. This guy, I put it back inside. And now it's, again, a sum index over delta plus. Like that. And the price that I pay, because the difference between this expression and that is a minus sign, is this minus here. What do we learn from that? So that's a conclusion of this whole computation, is that A sub SIW is minus A sub W. And that for every I. We also know, that I didn't circle in red, but here it is, that A sub, the identity element of the Weyl group, is 1. And therefore, A sub W is minus 1 to the length of W, which I'll abbreviate by minus 1 to the W. Now we're essentially done, and we have the so-called Weyl character formula, which tells us what the character of L lambda is, namely well, where is it? It's this, and I need to substitute. It's this formula where here I put minus 1 to the W. So on the numerator, I have a sum. Shifted action of the Weyl group on lambda. And on the denominator, I have a product. So this might look complicated, but it's a very powerful formula. I mean, these weight multiplicities very quickly become very big numbers, and it's not manageable to try to just compute all these weight multiplicities for everything. But that formula is a very concise way of packaging it all. If one takes lambda to be equal to the trivial representation, then one learns something else, which is that this denominator, well, if lambda is a trivial representation, the character is equal to 1. Character is defined to be this sum of these dimensions times these things. Well, the trivial representation has only one weight space, which is one-dimensional, which lives in weight mu equals 0. So that term is e to the 0, which is 1, and that term is 1. So you get the character is the constant function 1. Well, put here lambda equals 0, and you get a rather non-trivial equality between this and 1. And what that allows you to do is to say, well, this denominator, actually I can rewrite it as a sub over the Weyl group, alternating things, this W acting the shifted action on 0. So that's another form of the Weyl character formula, which is also often used. Okay. So now I want to go on to quantum groups. This was essentially all I needed from the representation theory of finite dimensional Lie algebras. Let me resume what we've seen. We've seen that for every element in lambda plus, so lambda plus is this cone here. All these, so here lambda, this lambda here is 1, 2. And the set of all possible lambdas where you have positive numbers here, that's this lambda plus. So there is a bijection between representations and points of this cone. We know that every representation is a direct sum of some of these. So that gives a complete understanding of the category of representations. Well, what were we doing this for? If you remember in Chris's lectures this morning, what he wanted was to find some interesting categories and to say, I want to have a 1, 2, 3 theory where the circle manifold goes to that category, and then cobordisms go to certain functors, and then 3 manifolds go to certain natural transformations. And by doing certain formal manipulations, he could establish that the category, the value of the circle, should be a category with finitely many simple objects. So here we have a nice category, but it has infinitely many simple objects, namely 1 for every element of lambda plus. And that's the whole point of quantum groups. Quantum groups is a variant of this whole story where this infinite set gets cut to a finite set. So what you end up having is you end up having a line that lies like this, and the only representation that survive are the ones below the line, and the ones above the line no longer exist. And then that category of representations of the quantum group is the thing that you can then use to build the TFT. Okay, so I will now just give the definition of the quantum group. The quantum group, well, it's called quantum group, but it's really not a group. It's an associative algebra. It is an algebra that looks a bit like the universal enveloping algebra of the Lie algebra. And here I wrote down the presentation of that algebra. If you interpret that presentation as a Lie algebra presentation, you get G. If you interpret that presentation as an associative algebra presentation, you get this. And the quantum group is denoted U sub qg. And it's going to be an algebra which has a presentation that looks very much like that one, except it's going to be, well, it's going to be tweaked a little bit. So it's going to depend on this parameter q. If we set q equal to 1, then we recover this guy. So these elements hj, I mean, they're formal elements, but it's useful to think of them as functions on the weight lattice. I mean, look at this picture. How does h1 act? Well, it acts by, well, each weight space gets mapped to itself by a given number. So that is a function. It's the function on this lattice which takes the value 1 here, the value -1 there, the value -2 there, and so on. Then we can rewrite these relations as so let's define the operator T sub alpha I to be the thing that shifts the function. The function hi and the function hi plus aij, well, you can think of it as being like adding aij, but actually it's better to think of it as being like shift by alpha I. And for any function, if I have any polynomial in the hi's, then this relation is going to be satisfied for that polynomial. Take this to be the polynomial in the hi's, then it satisfies that. In UQG, we'll be working with some other generating set for the functions on this weight lattice. Namely, ki, which is by definition q to the di hi. Di is this number that remembers whether it's a short root or a long root. It's this number that's equal to 1 if there's no double lines in the Dynkin diagram, 1 or 2 if there's double lines somewhere, or 1 or 3 if it's type G2. Okay, well, hi is a function on lambda, so it makes sense to take this as a function, new function. It's a function with values. So it's a function it's better, I mean, you can view Q as being a particular number, in which case it's a function with values in C, or you can view Q as being a formal variable, in which case it's a function with values in, well, actually, Laurent polynomials. So Z adjoint Q, Q inverse. And this way of understanding those relations allows you to rewrite corresponding relations for these variables ki. Here, let me put here J. So that it agrees with this. So this is one of them, and there's another one for Fi, which is Ki Fj equals Q to the minus di Aij Fj Ki. Okay, so I'm slowly writing down the relations that are used for the definition of this. So let me write the relations that correspond to this very first one. That is Ki Kj equals Kj Ki. That's not very surprising. You want these functions to commute with each other. Then we have this that corresponds to the first one, that corresponds to the second one. These are, in some sense, the easy relations. All the meat is what happens with those three relations. That's really the relations that are where something is happening, where you're really doing something. Okay, so the generators of this guy are called Ki, Ei, and Fi. Ki is just a formal generator, but you should think of it as being this. And they satisfy some relations. Here are some relations And there's going to be 3 more relations corresponding to this, to that, and to that. But I can't just write them down like that now. I need to do some preparations. Okay, so I'm going to give some unmotivated definitions. So if n is a number, a natural number, then I defined square brackets n sub q to be q to the minus n minus 1 plus q to the minus n minus plus 1 plus 3 plus and so on plus q to the n minus 3 plus q to the n minus 1. This can be rewritten in a more concise form as q to the n minus q to the minus n divided by q minus q inverse. So 1 is just 1, 2 is q inverse plus q, 3 is q to the minus 2 plus 1 plus q to the square, and so on. These are so-called q analogues of, well, in this case, numbers. I'm going to have q analogues of binomial coefficients very soon. If you set q equal to 1, you recover the usual notion. And that's what we want. We want a thing such that if we set q equal to 1, we'll recover this guy. Okay. The q factorial is defined as the product of the above expressions. Fair enough. You're allowed to do that. And the q binomial, n choose r, is defined to be well, it's the same expression as the usual definition of the binomial, or at least one of the definitions of the binomial, except you replace it by those funny notions. And right now, the only thing you can say is that if you replace q equals to 1, I recover the usual binomials, but there's really no guarantee that this is a good thing to do. I mean, if you write down some random formulas and say, let's study those things, there's really no guarantee that you get something reasonable. So I should at least do something to argue that this is a reasonable thing to do. So let me so you probably know the standard recursion formula for the binomial coefficients. And there's a q analog, which is that n choose r equals q to the minus n minus r. Let's see, I don't have very much space. I'll make some more space. So that's a usual relation that you use to draw the Pascal triangle. Like, you draw the Pascal triangle, and this term is the sum of the two that are above. If you set q equals to 1, these two terms go away, and you're left with this equals that plus that. So let me show you why that is the case. So we need to argue that n factorial okay. Okay, this is what I've just substituted the definition into what we're trying to do. Well, let's take that equation, and that equation is equivalent via the operation of multiplying by r factorial n minus r factorial divided by so we divide by n minus 1 factorial. That removes this numerator, removes that numerator, and we're left to just n here. We multiply by this, that kills this denominator. Well, let's see what happens with this denominator there. This denominator, we multiply by something that contains a little bit more. There's the term r that remains. So we end up with this. And on the other side, there's the term n minus r that remains. And it's actually fairly easy to check that this is a relation that's satisfied. This is just a sequence of powers of q in a row, and that's another sequence of powers of q, and then I shift them so that they land next to each other, and then I have a sequence of length this plus that, which is exactly this. So that's a proof of this lemma. So now that I have those guys at my disposal, I can tell you what the relations are that replace those. So the relations over there are called the Serre relations, and the ones that I'm going to write down are called the quantum Serre relations. So if I and j are different, you get 0. That doesn't change. But then you get this. Here I've omitted the number q. The number q is actually important. Here we want this with q to the di. So what do I mean by that? H is a function on the weight lattice lambda. And I apply this definition just pointwise to all the entries on the function. It turns out that if you do that, you end up with delta ij ki minus ki inverse divided by q to the di minus q to the minus di. So you end up with an expression that is algebraic in terms of the ki's. So that's a reason why we don't work with the hi's, but we work with the ki's. It's because the expressions are algebraic in terms of the ki's and are not algebraic in terms of the hi's, and we want to do algebra. We don't want to do some kind of mixture between analysis and algebra. So this part here is sort of motivation. But actually the relations is this equals that. And thinking of these elements, hi and kr, as functions on the weight lattice, well, that's the way you should think of them, but they're just abstract elements of this abstract algebra. Okay, I have now time to finish this one. So let me rewrite this relation by just expanding everything. What does it mean? I mean, if I just write EI, 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 and then EJ minus EI, EI, EJ, EI, and so on. So if you expand it, you end up with the following sum. Sum r equals 0 to a ij plus 1 minus 1 to the r aij plus 1 choose r ei to the aij plus 1 minus r ej Okay, there's the corresponding, for f is completely identical, so I won't treat it. Here what I wrote is not the quantum Serre relation. Here what I wrote is word for word the usual Serre relation, the classical Serre relations. Now I'm going to modify it to make it quantum. Well, you don't change anything, you just change its binomial coefficient. And then you need to think a little bit about what you take as your variable, and it turns out that it's not q, but it's q to the di, d sub I. So that's this number that's equal to 1, 2, or 3, depending on what kind of Dynkin diagram you have. That's it. So circled in green, I have so that's the presentation of UQG. It's an algebra generated by KIs, EIs, and FIs subject to the KI's commute. This is just saying that you can think of KIs as providing a grading by the weight lattice, and then those relations. I'm out of time, but I would like to nevertheless write down what a representation looks like for SL2. So we have now E, F, and k. As before, E goes this way. Yes?
But you also added in this equation another generator that we didn't have before, right? This Ki inverse that really wasn't there.
You're right. So if you want to be super picky, you need to say that you add a generator Ki inverse with extra relation Ki times Ki inverse is 1 and Ki inverse times Ki is 1. And if you want to be super, super picky, then you need to say that you're not allowed to divide by Q's, but you need to add an extra generator which sort of is a placeholder for this expression, and then that generator times this thing is equal to the numerator, and then the relation, anyways. So yes, you need to do all that if you want to be super precise. So K acts by Q to the 0, Q squared, Q to the 4th, Q to the minus 2, Q to the minus 4. E acts by, well, before it was 1, 2, 3, 4, and 1, 2, 3, 4. Well, now these get replaced by the Q analogues. And, well, it's actually a cute little exercise that I want to do to check that the relations, all these relations that I have there, are satisfied in this example. This relation here, this only exists when I is not equal to j, and therefore is completely irrelevant for SL2. So, but that relation, this relation here, is the one that's interesting to check. That's, I'll leave that as exercise. Okay.